Hello students, in last lecture we have studied the concept of metric and metric space. We have also taken concept of visual metric defined on set of numbers. Then we have defined other functions which satisfy conditions of metric or which doesn't satisfy conditions of metric. Means we have studied some few examples of other metric other than visual metric and some functions which are not metric. Today, in our next second lecture, we'll study more examples of metric. So, see the next example here. Let x be an empty set. Define d from x cross x to r as d of xy is equal to 1 if x is not equal to y and it is 0 if x is equal to y. Then show that D is metric for x. This metric is called a discrete metric. Discrete metric for x and set x together with d, which is x to the suffix d, is called as discrete metric space. Or sometimes it is also called as standard discrete metric space. Now we'll see its solution. So first exam, by definition of d of xy greater or equal 0 for every xy belongs to x, because d of xy takes 1 or 0 value. M2, again by definition of d of xy is equal to 0 if and only if x is equal to y. Third, by definition of d again, d of xy must be equal to d of yx. Because if x not equal to y, then d of xy is 1. In this case, y is also not equal to x, means d of yx also becomes 1, and d of xx is 0, means d of xy is equal to d of yx. Now, we have to prove triangle inequality. Triangle inequality. To show d of xy less equal d of xz plus d of zy for any xy z belongs to x. So here we have to take cases. Case 1, if x is equal to y, then left hand side d of xy is equal to 0 by definition of d. Right hand side d of xz plus d of zy is greater or equal to 0, since d of ab is 1 or 0 greater or equal to 0. Means this implies d of xy less equal to d of xz plus d of zy for x is equal to y, and whatever z may be. Case 2, if x not equal to y, then left hand side is d of xy takes one value. For RHS, d of xz plus d of zy, this will become 1 plus 1 is equal to 2 if x not equal to y not equal to z. d of xz plus d of zy, this is equal to 1 plus 0 is equal to 1 if x is equal to z, z not equal to y. Oh, x not equal to z, z equal to y. d of xz plus d of zy, it takes 0 plus 1 when if x equal to z, z not equal to y. From these cases, this satisfies this triangle inequality. From these cases, d of xy must be less equal to d of xz plus d of zy for every x, y, z belongs to x. Thus, these satisfy all axioms of matrix. And therefore, it is matrix space. This matrix D is called as discrete matrix for non-empty set X, and X together with discrete matrix is called as discrete matrix space or standard discrete matrix space, which is a very important example in matrix spaces, because for counter examples, this example plays very important role while getting contradiction in some results related with matrix space. Now in this example, if I take other function in following ways, for x not empty set, d of xy is defined as 0 if x equal to y and it is k greater than 0. Then xd is matrix space. So in previous example, I am just replacing 1 by k here, where k is any non-zero fixed real number which is positive. Then d of xy is greater or equal to 0 by definition of d again. d of xy is 0 if and only if x is equal to y. d of xy is equal to d of yx again. For triangle inequality again, by same cases here, just this one will get replaced by k, and triangle inequality is also satisfied by this function. So this x together with d function is a matrix. This is also known as discrete matrix space. This is also called as discrete matrix space. So whatever positive value of k may be here, it is matrix. Now here we have taken examples on set of real numbers. What about the complex number sets? If x is equal to set of complex numbers, Then d of z1 z2 is equal to mod of z1 minus z2. z1 and z2 are complex numbers. Then whatever them for set of real numbers or number set on same line, that C together with D is metric space. Then set of complex number with D function is metric space, and this is the usual distance, therefore C is metric space, which is the usual metric space. For R, I have taken example d of xy is equal to mod x cube minus y cube. Is D metric for C? So we know that any nth degree polynomial has n distinct roots in set of complex numbers. So z cube is equal to 1 has 3 complex roots. So we know that 1 cube is equal to minus 1 plus I root 3 by 2 its cube is equal to 1. Complex cube roots of unity are nothing but 1 minus 1 plus minus I root 3 by 2, which I have studied in secondary level, or while studying quadratic equations you come across complex cube roots of unity. So with help of this, from this d of 1 and minus 1 plus I root 3 by 2, this becomes 0, where these two numbers are not equal. This implies D is not metric for C. You know that d of xy is equal to mod of x cube minus y cube. xy belongs to R. Then RD is metric space. So yesterday we have verified this. But if I take the same type of function defined on complex number, it is not metric. So concept of metric depend on its definition as well as underlying set X on which you are defining that metric. Note this point, it is too important. Okay, now we'll study some metrics on R2 or XY plane. Let X is equal to, or we'll take directly Rn. It is set of vectors x bar is equal to x1, x2 up to xn. X size belongs to R. 1 less equal I less equal n. Define for x bar is equal to x1, x2 up to xn. Y bar is equal to y1, y2 up to yn belongs to Rn. We'll define D as d of x bar, y bar is equal to, or I'll take d1 is equal to summation of I equal to 1 to n mod of xi minus yi. Component wise subtraction and their modulus and then their sum. I am taking it as distance function defined on Rn. Then Rn together with d1 is metric space. So we'll justify or we'll verify how d1 satisfy all conditions. Okay. So first, or for this first we will choose 3 vectors in Rn. Let x bar is equal to x1 x2 up to xn, y bar is equal to y1 y2 up to yn, z bar is equal to z1 z2 up to zn belongs to Rn. Then first d1 of x bar y bar, which is nothing but summation of modulus of xi minus yi, I equal to 1 to n. This must be greater equal 0 since mod of xi minus yi greater equal 0 for every I. I varies from 1 to n. Second, because xi and y are real numbers, d1 of x bar y bar is 0 if and only if, by definition of d1, summation of I equal to 1 to n mod of xi minus yi must be 0. So this is sum of non-negative numbers, and sum of non-negative numbers is 0 if and only if each term in that sum must be 0, means mod of xi minus yi is 0 for every I equal to 1 to up to n. As this is 0 for every I, and we know that mod of a minus b is 0 if only if a equal to b, so we'll get xi is equal to yi for every I equal to 1 to up to n. So for these two factors, their components are same, therefore they are equal, so x bar is equal to y bar. Therefore d1 satisfy positivity axiom. Third, symmetry. d1 of x bar y bar is equal to summation I equal to 1 to n mod of xi minus yi. I can write this as summation of I equal to 1 to n. We know that mod of a minus b is equal to mod of b minus a. Therefore, this is same as summation mod of yi minus xi. Then by definition of d1, this is nothing but d1 of y bar x bar. Thus, d1 satisfy symmetry axiom. 4. Triangle inequality. For this, mod of xi minus yi, I can write as I have to relate x bar, y bar to x bar, z bar and z bar, y bar. So, their components xi minus y are real number. In this, I will insert the ith component of z bar factor, that is zi, as mod of xi minus zi plus zi minus yi, and then again treating this xi minus zi as one real number, zi minus y as second real number, and using triangle inequality of real numbers for absolute value function, we get this is less equal mod of xi minus zi plus mod of zi minus yi. Now taking summation on both sides, we'll get summation of I equal to 1 to n mod of xi minus yi. This must be less equal summation of xi minus zi plus summation of I equal to 1 to n mod of zi minus yi. Then by definition, we will get d1 of x bar y bar less equal d1 of x bar z bar plus d1 of z bar y bar. Thus, d1 satisfy all axioms of metric. d1 satisfy all axioms of metric. Therefore, Rn together with d1 is metric space. where this n is greater equal to 2. N greater equal to 2. Now again, if I take other example, next example, take x equal to Rn containing n tuple vectors. Then I am defining now d2 function on it. d2 summation of I equal to 1 to n xi minus yi bracket square whole thing raised to half. Then Rn with respect to d2 is also matrix space. For this again we will take these three vectors in Rn. Okay. So here d2 of x bar y bar is summation of I equal to 1 to n xi minus yi square raised to 1 half. This is again greater equal 0 because square of any real number is greater equal 0 and then its square root is also positive. d2 of x bar y bar is 0 if and only if this summation xi minus yi bracket square raised to half is 0. This implies by taking square, this implies or if and only if summation of xi minus yi is square I equal to 1 to n, this must be 0. But then from this every xi minus yi square must be 0 for every I equal to 1 to up to n, and we know that this implies xi minus yi square root of 0 is again 0, will get xi minus yi is 0 for every I equal to 1 to up to n. So we will get xi is equal to yi, which implies x bar equal to y bar, and reversely. For third exam, d2 of x bar y bar will get again summation of xi minus yi bracket square raised to 1 half. Again, xi minus yi square is same as yi minus xi square, so I just write this as y minus xi square and its square root here. Then we will get it as d2 of y bar x bar. Now we have to prove triangle inequality. It is different from this. This adjustment doesn't work there. For this, d2 of x bar y bar will take its square. Will take its square. This is equal to summation of xi minus yi bracket square I equal to 1 to n. Now insert here ith component of z bar vector, that is zi, as follows. Summation of I equal to 1 to n xi minus zi plus zi minus yi its square. Now I will take this xi minus zi as ai, this as bi, then this is equal to summation of I equal to 1 to n ai square plus bi square plus 2 times ai bi. We will separate that sum. This is equal to summation of ai square I equal to 1 to n plus summation of bi square I equal to 1 to n plus 2 times summation of ai bi I equal to 1 to n. For this we will take it as 1. Okay. Now by Cauchy-Square inequality, inequality, a bar dot b bar is less equal norm of a bar into norm of b bar. That is for A bar is equal to A1, A2 up to An, B bar is equal to B1, B2, Bn belongs to Rn. This is summation of Ai, Bi, I equal to 1 to n. This is less equal. Summation of Ai square raised to half. I equal to 1 to n into summation of Bi square raised to half. I equal to 1 to n. Using 2 in 1, I will get d2 of x bar y bar its square is less equal. Summation of ai square plus summation of bi square plus 2 times summation of ai square raised to half into summation of bi square raised to half. But this is nothing but summation of ai square raised to half plus summation of bi square raised to half whole thing square. Taking I equal to 1 to n everywhere. Now, this is by substituting now, ai is equal to xi minus zi and bi is equal to zi minus y. But before that, we will take square root. We will take square root. Taking square root, we will get d2 of x bar y bar is less equal summation of ai square raised to half plus summation of bi square raised to half. Again resubstituting the values, this is equal to summation of xi minus zi its square raised to half plus summation of zi minus yi its square raised to half. Which is equal to, by definition of d2, it is nothing but d2 of x bar z bar plus d2 of z bar y bar. Thus d2 satisfies triangle inequality, and therefore d2 is metric for Rn, and therefore Rn d2 is metric space. This is the second metric we defined for Rn. Now we'll define one more metric for Rn, which is the third metric. Let Rn is equal to again set of x bar is equal to x1, x2 up to xn. Xi belongs to R. For x bar is equal to x1, x2 up to xn. Y bar is equal to y1, y2 up to yn. Belongs to Rn. D infinity of x bar y bar will define it as maximum of mod of xi minus yi, where I runs from 1 to n, 1 less equal, I less equal n. Then Rn together with D infinity is metric space. Here n greater equal 2. For this again, we will take three vectors in Rn. So let x bar is equal to x1, x2 up to xn, y bar is equal to y1, y2 up to yn, and z bar is equal to z1, z2 up to zn belongs to Rn. As to prove triangle inquiry, I require three arbitrary vectors, so I am taking three different vectors from Rn notations. Then a monoaxiom, since mod of xi minus yi greater or equal to 0 for every xi yi belongs to R, implies maximum of mod of xi minus yi 1 less equal I less equal n must be greater or equal to 0, implies d infinity of x bar y bar greater or equal to 0. M2, d infinity of x bar y bar is 0 if and only if maximum of mod of xi minus yi 1 less equal I less equal n is 0. Now maximum of that n terms, n numbers is 0, and in which mod of xi minus yi is non-negative number for each I. So each term in that set must be 0 for every I equal to 1 to up to n, since mod of xi minus yi greater or equal to 0. Mod of a minus b is 0 if and only if a equal to b, that is the property of distance between two numbers. So this is if and only if xi is equal to yi